Hello and good day. So, I want to make an explanation on one of the algorithms that we used in solving problems in lit code, basically solving problems in data structures and algorithms. It's one of the foundational algorithms which can be applicable to several problems. So, that algorithm is the binary search. So, it's a case of if you're looking for a particular number, how quickly can you find that number in in an array. So it's on the case of it presupposes that you have to sort the array, and once it's sorted, then based on the ordered arrangements of the numbers that are in the list, you can easily find the position where that number is by halving um, the list and continuing the halving of the list. So the complexity, the time complexity is O log n. It's going to be O log n complexity. So let me just write the algorithm. So it's going to be binary search, and then you have the numbers, and then the target number that we're looking for. So, like I said, it's on the supposition that the numbers has to be sorted, and then so we have the left index. So you are going to use two pointers in the array. So, for example, if you come here now, when it's already sorted, actually, so there should be the left pointer here at this point, which is 0, and then at this index, which is the length of the array minus 1. So this array is 1, 2, 3, 4, 5, 6, 7, 8. So this point should be 7. So we have our right is equals to the length of the numbers minus 1. So we are going to sort it, like I said. So we are going to sort it. It's going to be in this format now. So if this insert is going to be 1, 2, 3, 5, 7, 8, 11, and then 15. So I think it is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So it's already sorted in this way. So we have the left pointer here, and then our right pointer should be around here. So let us assume that the target we're looking for is 7, right? So let me just write it. The target is 7. So now that it's sorted, the position of where this 7 is 0, 1, 2, 0, 1, 2, 3, 4. The position here, the position of this is actually 4. But we are going to use this algorithm to be able to find it. So we now say while left is less than or equal to right. So we are going to be moving the pointers until there's a position where the left and right gets equal. That is where you're going to stop because the left cannot be more than the right. So it depends on the conditions we have, whether you're going to move either the left pointer or the right pointer. So we have our mid, the mid index we're going to use is equal to the sum of the left plus right divided by 2. So we're using this pattern of division so that you're not going to have like an overflow or like you're not going to have decimal um, point. So it's going to be like a whole number in our division. So this will give us, in this particular case, the length of this is um, 1, 2, 3, 4, 5, 6, 7, 8. The length of numbers is equal to 8 actually, is 8. So we can easily have this 1, 2, 3, 4. So this should be the mid. So if you say 0 plus 8 minus 1, which is 7, 0.7 divided by 2. So 7 divided by 2 will give us 3. So the mid in this case is going to be on the third position, which is 0, 1, 2, 3. At this pointer, at this pointer, 0, 1, 0, 1, 2, 3. This should be our midpoint. This should be our mid. And then this should be our left. This should be our left. And then this should be our right. Remember, what we're looking for is 7. Now, after doing this now, our mid is already at the index position of 3. We now say if our numbers of mid, what number is in that mid position? It's actually 5. If it is equal to our target, we're simply going to return that index. But in this case, it's not equal to. So we say else if the numbers of the mid is less than our target. This should be S. Is it less than our target? The numbers of the mid, it's less than our target actually. It's less than because our target here is 7. But numbers of the mid, which is at the index position of 3, is 5. 5 is less than our target. So we are going to move the left pointer by 1 after the mid. So it's going to be our left is equal to mid plus 1. Then the other condition is else if numbers of mid, had it been it was greater than the target, had it been our mid is greater than target, maybe our target was at point 3 now, we're going to move our right by mid minus 1 to come at this position. So I just want to finish up the function here. So it's going to be right equals to mid minus 1. Then if that number is not, this target number is not in our list, we're simply going to return minus 1. So like here now, we are going to move this now. The left is going to be mid plus 1, and the mid plus 1 is at this position, which is here. So this should be our new position for our left. I'm going to remove this here. Let me see this one. So our left now is here now. Now left is still less than right. Okay. So we are going to, since we already shifted it, we're going to divide it again to get our mid position. So our left is now, remember, our mid is 3. So our left now is going to be 3 plus 1, which is 4. Our left is going to be 4, and our right is going to be still 7, I suppose, because the length of this is 8. So 4 plus 7 is 11. So 11 divided by 2 will give us 5. So our new mid is at the position 5, which is 0, 1, 2, 3, 4, 5. This should be our new mid. So our mid is here now. Remove this. Remove this. Now we're going to check if our mid equal to the target. It's not equal to the target. Then is our mid, numbers of the mid less than the target. It's not less than the target because this is the mid, which is 8, and our target is 7. So we're going to skip this one and come over here now. Our mid, the number at the mid index greater than the target. Yes, it's greater than the target because 8 is greater than the target, which is 7. So we're going to our right is going to be mid minus 1. So you are going to move this to mid minus 1, which is now um, at this position where the left is. So because our mid is 0, 1 at the position of 8, our right is going to be mid minus 1, which is going to be this position. So we're going to have our right here. Our right should be here. So we're going to remove this. I think I should just put this thing here. Okay. So now we are going to now perform the operation again. Mid is going to be left plus right divided by 2. Now at this position, now our left is equals to right. It's our left is not above right now. I think this should be the last operation we're going to perform now. So our left is 0, 1, 2, 0, 1, 2, 3, 4 at position 4, plus our right is the same position, which will give us what? 8. So now we are going to do 8 divided by 2 is going to give us 4. So this is our new mid. So our mid now tallies with both our left and our right, which is at this position now. This is our mid. So we're going to remove this. Then remove this. So we say if our numbers of mid is equal to the target, check it. Our numbers of mid now is position 7, and our target is actually 7. We're going to return mid, this index position. 0, 1, 2, 3, 4. So we're going to return 4. So the while loop terminates here. So if you run this and add target equals to 7, it's going to give us 4. So this is actually how the binary search works. So it first of all sorts it and then continues to move the left pointer and the right pointer till it gets to the target point. So it's not something you're going to waste a lot of time finding the numbers. So for example, if it's a very long list and we have our target maybe like 51, and we have a midpoint at 50. If our midpoint is less than the target, we're going to remove all the 50 and just move our left to the midpoint plus 1. So it chunks up, it knows that the bulk of the 50 goes out, and we're going to deal with from 51, from 50 towards 100. So it's very rapid way of finding out the value you're looking for instead of counting one by one. So you see that the log, if you use that the NON, it's actually more tedious than O log n, which is for the binary search. So O log n for our time complexity is much better than ON. So like for example, one of the places where you can apply this binary search is if you're searching for um, a word in a dictionary. You're doing binary search without you even knowing that's what you're doing. So if you're looking for like omelette, because the dictionary is already ordered from A, B, C, D to Z. Since you're looking for omelette and the word you're looking for is O, so there's no point for you to start searching for um, omelette from A or B or C. What you need to do is to simply find out the numbers that are before O, which is ABC till N, and just leave N. You're not bothered with searching that. You just start with O and start searching. And when you even come with the omelette, since it's going to be OM, so there's no point for you to searching for OA, OB. You just come to the point where there is OM and start searching. When you come to OM, look for E. There's no point searching for OMA, OMB. Just go to E. Before you know it, you get to the answer of omelette. So you're really performing binary search in the search of words in dictionary without you even knowing. So this is one of the beautiful things about algorithms. It helps us in even solving real life problems. Once you learn how to be able to solve problems algorithmically, you're going to see problems from a different perspective and it makes you to think more logically and be able to tackle your problems and solve them. So this is just like a brief explanation on how to work with binary search.